Okay, so first I want to come up with a little mnemonic for remembering this. So we're going to have a sort of a little poem here for our algorithm. All right, so our algorithm for solving separable differential equations. We'll write that, solving separable differential. Whoops, equations. Let me do a better job than that. Equations is the following, okay? Sometimes we're going to add a previous step, so I'm going to leave room up here, but basically we do the following. We separate, we integrate, and then we isolate. And just to make things rhyme, sometimes before we begin the separation process, this is a sometime step. I just call it algebrate. In other words, do algebra to set us up for the problem before we try to separate. So sometimes we algebrate, we always separate, integrate, isolate. So that's a good way to remember what it is that you need to do. So let's look at a couple problems here. All right, so let's start with example 1. Which will be a pretty easy example. Let's start with dy dx equals 2x. Okay, so if we had that, we could actually already, we're ready to separate it. Okay, so I'm going to write the following. I'm going to write that dy is equal to 2x dx, right? So now we have it in a form where we could turn it into an integral. I could integrate both sides, okay? So we separated it, and now we're ready to integrate it. And we can do that, but remembering this is really, we're integrating 1 with respect to y. So the antiderivative of 1 with respect to y would just be y. And then the antiderivative of 2x with respect to x is x squared. Now, technically, when you integrate, you should have plus c on both sides, all right? But we're only going to put plus c on the right-hand side. The reason for that is if you had an unknown constant on the left and you had an unknown constant on the right, the first algebraic thing you would do is subtract the constant on one side to get it to the other. And so we'll just group the constant together as a single constant. In general, when I'm doing, when I'm solving differential equations, I put the constant in place after I finish the last integration. Okay, so the answer is simply this. All right. Now that could have been done simply by starting with the original problem. Since we had dy dx, we could call that, f prime of x equals 2x. So this is really nothing new. If we integrate f prime of x with respect to x, then we should integrate 2x with respect to x. And then what we have when we finish is what f of x should equal x squared over 2 plus c. I'm sorry, just x squared plus c. And what is f of x? Well, if dy dx is f prime of x, then y must be f of x. So we really have done the same problem. What's far more interesting is the next example. Okay, so then when dy dx is simply a function of x, we really could have just integrated the right-hand side. Here's an example where we can't just do that. Take the same problem, but have dy dx equal 2 times y. All right, so we need to separate our variables. All right, and so what that means when we separate the variables is everything with y goes to the left, and everything that does not have y will go to the right. Specifically things with x, but sometimes I'll also leave or constants. I often will move those over to the right-hand side. We want the left-hand side to be as simple as possible, but everything involving y must be on the left-hand side, right? So when we separate this, dy certainly has y, but the y that is on the right, we need to move to the left by dividing both sides by y. The 2 that's on the right will stay on the right. The dx that was in the denominator on the left will move to the numerator on the right if we were to multiply both sides by dx. So now I have a separated differential equation. Okay, so I did step 1, I separated. So step 2 is to integrate. All right, so throw that integral sign in there. All right, and you should be aware, just let me write this on the side, that the integral of dy over y is the same as saying the integral of 1 over y integrated with respect to y. Okay, so we could say it either way, and hopefully you know that the antiderivative of that would be ln of y. Could have been 1 over x with respect to x, the antiderivative would be ln of absolute value of x. So the left-hand side now becomes ln of the absolute value of y, right? The right-hand side will become 2x plus c. When you integrate 2 with respect to x, you get 2x. If you take the derivative of the right-hand side, you get back to 2. You take the derivative of the left-hand side, you get back to 1 over y. So those are the correct antiderivatives. So we have now done step 2. We integrate it. So we we separate it and integrate. Let me write those down. Separate. It's kind of what we did between these 2 steps, and then we integrate to get from the middle to where we are now. Okay. Now, the last thing we need to do is isolate. And by that, I mean, let's find what y is. So y is our variable. That's our target. We need to solve for it. So to solve for it, we need to isolate for the output variable. So we're going to isolate y. Well, how do you get y by itself? It's inside of a natural log. So we can say, and it's inside of absolute values. So we can say the absolute value of y is equal to, how do you undo a natural log? You make it the exponent of e. So if we undo the natural log on the left, it means we are taking the right-hand side and making it the exponent of e. Exponentiating it, actually, would be a way of saying that. So we can exponentiate both sides. All right, now we still need to figure out what y could be. Oh, well, let's go another step here, doing a little more algebra, using, let me write a rule of logarithms on the side. If you have e to the a plus b, that's the same as e to the a times e to the b. All right, so I can say that the right-hand side here is equal to e to the 2x times e to the c. Okay. Now let's remind ourselves that e to the c is an unknown constant. So e to the c is an unknown constant as well. So I'm going to call this first constant c1, and then e to the c will be, we are going to rewrite that simply as c. I'm going to bring it over here because we want to put our constants in front. We still have e to the 2x, and we still have absolute value of y. All right, so e to the c1 is a constant, and we'll just call that our new constant c. All right, it's not the same, c and c1 would not be the same numbers, but since c1 was an unknown number, e to the c1 is an unknown number, and we'll just consolidate all of that as c in front. Okay, now we have to still get y. Hopefully you know that if y, we take the absolute values away, then when y is whatever is on the left-hand side, I'll just pause for a second and figure out how I want to state this. Yes, this is how we could state this. You could say if y is positive, y is, you can just remove the absolute value sign as c e to the 2x. And if y is less than 0, then negative y equals c e to the 2x. Now, here's the beauty of this. We never specified if the unknown constant C were positive or not. It probably is, okay, because when we're looking at this, we have, I guess actually we could have an exponential growth that goes downward, but e to the c is probably going to be a positive number. But the point is, since we haven't specified yet whether c is a positive or negative number, we can absorb the negative sign that's over here on the left as part of the constant, and just write that y is equal to a constant times e to the 2x. We could write plus or minus a constant times e to the 2x, but since the constant is unknown in sign as well as size, we'll just say it's c times e to the 2x. So we have just shown that the solution to this is in fact an exponential growth kind of function. So that's what we have here. Okay. Now C is unspecified. This is called, what we talked about before, the general solution to the problem we just had. Okay. So this is the solution to what we just had. If we needed to check this, all right, so if we did want to check it, we did this in earlier videos, we would find dy dx is equal to 2c e to the 2x, and then we would sub back into dy dx equals 2x, and we would see that this is in fact going to be true. We're not going to go into that now. Okay. What we want to look at now is what about the specific solution or the initial value solution. Okay. What is the initial value solution? If the curve passes through let's just say 0, 2, right? Well, we simply sub the initial values in. Okay, so 2 will go in for y, c is still c, e to the 2x becomes e to the 0, so c must be 2, so y equals 2 e to the 2x is the value, the solution to the initial value problem that passes through 0, 2. Okay, so there's a second example. Let me move on to a third example that's very similar. Okay, what if we had the following dy dx. Oh, I'm going to change this a little bit, and we want to put in plus, what do we have there? 2y equals 0. Okay, so we can't isolate this yet. So this is where the algebraic comes in. But it's very simple algebra. We need to write this in a form where we will be able to isolate it. Okay, so now we'll be able to, so we've written in a form where we will be able to separate it. So now this can, when we need a negative sign here, because we'd have to subtract 2y from both sides, now we can do what we did in the previous problem. So I can rewrite that dy over y is equal to negative 2 dx. So now it's in a form where we can integrate and isolate. All right, so why don't you pause the video and see if you can integrate and isolate this. Okay, so I'm going to work out the solution relatively quickly. So this will be ln of absolute value of y, just like in the last one. This will now be negative 2x plus c. I'll call that c1. How do we undo natural log? We exponentiate it. So absolute value of y is equal to e to the negative 2x plus c1. We're going to see this a lot. So we can say the absolute value of y is equal to c times e to the negative 2x. And since c can be plus or minus in value, we can simply say y is equal to c times e to the negative 2x. And that is my general solution. Hopefully you got the same thing, right? We won't worry about an initial value solution for that, right? Let's look at another one. Example 4. What if dy dx equals negative x times y? Okay, so this will be similar. Pause the video and see if you can write the separation step. Okay, so when you do the separation step, you should end up with dy over y is equal to negative x times dx. We need to divide both sides by y to get the y over to the left, and we need to multiply both sides by dx. All right, now you're in a position where you could integrate. So you throw in the integral sign. You could put the integral before or after the negative sign. The negative can be out in front. So you're ready to integrate. So at this point, pause the video and see if you can integrate that. Okay, so I'll do that quickly. ln of absolute value of y is equal to negative, when we integrate, we get x squared over 2 plus c. All right, so now you're ready to isolate. That means solve for y. We need to get y by itself. All right, so see if you can finish isolating. Okay, so this, I'm going to call that C1, by the way. So if we want to isolate, we exponentiate both sides and have e to the negative x squared over 2 plus C1, which, as we've seen in the last couple of problems, means that we get c times e to the negative x squared over 2. And since c can be plus or minus, we can write y equals c times e to the negative x squared over 2. And the plus or minus will be incorporated in the initial value that we're working with. Okay, so that's another example. It's relatively quick. Let me put example 5 over here. I'm going to put it over here because we actually can't solve this one. So we've seen that differential equation a fair amount. All right, we drew out its slope field. We drew solutions through its slope field. We sketched them in. We could have used Euler's method, taking little steps to get a pretty close answer. We could use MATLAB to use very small steps and get a very close answer to what the solution should look like. But we can't get an algebraic solution to this by separating variables. All right. The reason why is we really need to be able to use division or multiplication to separate. All right, so if we want to get y to the other side, we could do that. So let me just change color here. We could say this is y plus dy dx equals x. Looks like I've gotten closer to separating, but this dx is stuck underneath of here. I can't multiply by dx because if I did, I'd end up with y dx plus dy equals x dx. And now I'm still stuck with this dx here. How would I get rid of that? I divide by dx, but then that would just keep taking me back and forth between these two examples. Okay, so this is not separable. In fact, we can come up with a basic rule. If a function is separable, we can write dy dx is equal to a function of x times another function of y. So then we will be able to multiply both sides by dx. Okay, and so if I were to I probably should have left more room here. In fact, let me do that. Let me, erase and write my dy dx over just a little bit to the left. So we could multiply both sides by dx. and divide both sides by g of y. And we'll end up with dy over g of y equals f of x dx. Okay. Another alternative to this is that we have a ratio of those two things. So if I could rewrite it somehow with a little bit of algebraic manipulation, if I could write it as dy over dx equals f of x over g of x, then instead of, I'm sorry, over g of y, then we could multiply both sides by g of y, and that would work equally well. If I had dy dx is equal to g of y over f of x, we could divide both sides by g of y again. And in all of these cases, we multiply both sides by d of x to separate everything out. So when they're in one of these forms, basically one of these three forms, either f of x times g of x, f of x times g of y, or f of x divided by g of y, or a function of y divided by a function of x, we are able to separate them. But in the example 5 that we had, this is a function of x minus a function of y. You simply can't separate that. All right, in the next video, we'll just look at a few more examples.